With metabolic acidosis, acidosis refers to a process that lowers blood pH below 7.35. And metabolic refers to the fact that it's a problem caused by a decrease in the bicarbonate concentration in the blood. Normally, blood pH depends on the balance or ratio between the concentration of bases, mainly bicarbonate or HCO3-, which increases the pH, and acids, mainly carbon dioxide or CO2, which decreases the pH. The blood pH needs to be constantly between 7.35 and 7.45. And additionally, the blood needs to remain electrically neutral, which means that the total cations, or positively charged particles, equals the total anions, or negatively charged particles. Now, not all of the ions are easy or convenient to measure, so typically only 3 get measured. The dominant cation, sodium, or Na+, which is typically around 137 milliequivalents per liter, and the 2 dominant anions, chloride or Cl-, which is about 104 milliequivalents per liter, and bicarbonate, which is around 24 milliequivalents per liter. The rest are unmeasured. So just counting up these 3 ions, there's usually a difference or gap between the sodium concentration and the sum of the bicarbonate and chloride concentrations in the plasma, which is 137 minus 128, which comes from adding chloride and bicarbonate. And so you end up with 9 milliequivalents per liter. This is known as the anion gap, and normally it ranges between 3 and 11 milliequivalents per liter. The anion gap largely represents unmeasured anions, like organic acids and negatively charged plasma proteins, like albumin. So basically, metabolic acidosis arises either from a buildup of acid in our blood, which could be because it's produced or ingested in increased amounts, or because the body can't get rid of it, or from excessive bicarbonate loss from the kidneys or gastrointestinal tract. The main problem with all of this is that they lead to a primary decrease in the concentration of bicarbonate in the blood. Now, this can be broken down into 2 categories, based on whether the anion gap is high or normal. So the first category of metabolic acidosis is a high anion gap metabolic acidosis. In this case, the bicarbonate ion concentration decreases by the binding of bicarbonate ions and protons, which results in the formation of carbonic acid, which subsequently breaks down into carbon dioxide and water. These protons can come from organic acids which have accumulated in the blood, but they can also come from increased production in our body. One example is lactic acidosis, which is where decreased oxygen delivery to the tissues leads to increased anaerobic metabolism and the buildup of lactic acid. Another example is diabetic ketoacidosis, which can happen in uncontrolled diabetes mellitus, where the lack of insulin forces cells to use fats as primary energy fuel instead of glucose. Fats are then converted to keto acids, like acetoacetic acid and beta-hydroxybutyric acid. Another way acids can build up in our blood is due to an inability of the kidneys to throw them away, even though they're produced in normal amounts. This can happen in cases of chronic renal failure, in which organic acids like uric acid or sulfur-containing amino acids can accumulate because they aren't excreted normally. In other cases, organic acids don't come from inside our bodies at all, but instead they're accidentally ingested. These include oxalic acid, which can build up after an accidental ingestion of ethylene glycol, which is a common antifreeze, as well as formic acid, which is a metabolite of methanol, which is a highly toxic alcohol, or hippuric acid, which comes from toluene, which is found in paint and glue. All of these organic acids have protons, and at a physiologic pH, they dissociate into protons and the corresponding organic acid anions. The released protons attach to bicarbonate ions floating around, which decreases its plasma concentration and shifts the pH towards the acidic range. The key here is that the plasma maintains its electroneutrality, because for each new negatively charged organic acid anion, there's one less bicarbonate ion. And because the organic acid anions are not part of the anion gap equation, the anion gap will be high. In contrast, in other cases of metabolic acidosis, the decrease in bicarbonate ions is offset by the buildup of chloride ions, which are part of the anion gap equation, so the anion gap remains normal. The most common cause is severe diarrhea, where bicarbonate-rich intestinal and pancreatic secretions rush through the gastrointestinal tract before they can be reabsorbed. Another cause is type 2 renal tubular acidosis, which is the most common type of renal tubular acidosis, and develops because the proximal convoluted tubule, which is a part of the nephron, is unable to reabsorb bicarbonate. Other types of renal tubular acidosis also result in a normal anion gap metabolic acidosis, but the underlying mechanism is an inability to excrete protons in the urine. The excessive loss of bicarbonate results in a low plasma bicarbonate concentration, which ends up lowering the pH. In response, the kidneys start reabsorbing more chloride ions. So for each bicarbonate ion that's lost, there's a new chloride ion. This is why normal anion gap metabolic acidosis is sometimes called a hyperchloremic metabolic acidosis. Now, if there's a decrease in the bicarbonate concentration in the blood, which threatens to decrease the blood pH, the body has a number of important mechanisms to help keep the pH in balance. One of them is moving hydrogen ions out of the blood and into cells. To accomplish this, cells usually have to exchange a hydrogen ion for a potassium ion, using a special ion transporter located across the cell membrane. So in order to help compensate for an acidosis, hydrogen ions enter cells and potassium ions leave the cells and enter the blood. This might help with the acidosis, but it results in hyperkalemia. In cases, though, when there's a metabolic acidosis from excess organic acids, like lactic acids and keto acids, protons can enter cells with the organic anion, rather than having to be exchanged for potassium ions. Another important regulatory mechanism involves the respiratory system, and starts with chemoreceptors that are located in the walls of the carotid arteries, and in the wall of the aortic arch. These chemoreceptors start to fire when the pH falls, and that notifies the respiratory centers in the brainstem that they need to increase the respiratory rate and depth of breathing. As the respiratory rate and depth of each breath increases, the minute ventilation increases, which is the volume of air that moves in and out of the lungs in a minute. The increased ventilation helps more carbon dioxide move out of the body, which reduces the partial pressure of carbon dioxide in the body, which increases the pH. An additional mechanism is that if metabolic acidosis isn't caused by some renal problem, then several days later the kidneys usually correct the imbalance. The kidneys excrete more hydrogen ions while also reabsorbing bicarbonate ions, so that it's not lost in the urine. Alright, as a quick recap. Metabolic acidosis is usually caused by a decreased bicarbonate concentration in the blood. It can be classified into high anion gap cases, which are caused by the accumulation of organic acids, either due to their increased production in the body, decreased excretion, or exogenous ingestion. And the other type is normal anion gap cases, which are caused directly by a loss of bicarbonate ions, as is the case in diarrhea or type 2 renal tubular acidosis.